Good afternoon, everyone, and thank you so much for joining us. My name is Katie Rowley. I am with NOAA's Central Library here in Silver Spring, and we are very excited for our presentation today. Dr. Lauren Frey, who is joining us from Ypsilanti, Michigan, is going to be presenting on the Great Lakes hydrology research needs. A little housekeeping before we begin. If you do have a question, you are not allowed to speak. You are muted. So please place all questions into the chat or question panel, whichever one you see there, and we will get to them as we can. All questions will be held until the end of the presentation. So please get those in whenever you would like. If you do have a technical issue, as in you can't see the slides or you can't hear the speaker, I recommend you try logging off and logging back in. That usually solves most issues. If you are still having trouble, please chat at me and I will try to solve that for you. If all else fails, we are recording this and it will be posted on the library's YouTube channel after the fact, probably by tomorrow morning. And with that, I'm going to turn it over to Dr. Frey.
Okay, great. Thank you, Katie. Thank you for having me here to present this information. My name is Lauren Frey, and I am currently a visiting scientist with NOAA Great Lakes Environmental Research Laboratory. I'll be referring to that as GLERL as we go forward. My main job is with the U.S. Army Corps of Engineers Detroit District Office of Great Lakes Hydraulics and Hydrology. In that office, I am the technical lead for Great Lakes Hydrology. But over the past year, I've been on a part-time temporary detail working with NOAA as a visiting scientist, focusing on hydrology research to support their mission. And it's been a really great opportunity to work with them. We have a strong partnership between our two offices, which I'll talk a little bit about as we go forward. So in the talk today, I'm gonna give an introduction to Great Lakes water management and where hydrological research fits into that. I am going to spend some time talking about current basin conditions and the recent high water levels that we have now. I'll spend time talking about the research gaps that we have and how hydrological modeling fits in with GLERL's integrated modeling framework to address these gaps. And I'll specifically highlight a couple of important challenges related to estimation of precipitation and simulation of runoff with the National Water Model to enhance total water prediction. And then I do want to end by providing the latest Army Corps forecast, which was published earlier this week, so that folks who are interested can know what we're kind of looking at as the season pans out. But before I jump in, I do want to just point your attention to the image on this slide. I think it's a really, really great image of our majestic Great Lakes here. So for those of us who are in the Great Lakes, we know it well, but I'll spend a little time talking about the Great Lakes themselves for those of you who aren't from the Great Lakes region. So these lakes, we often don't think of it this way, but they're part of a large river system. They're part of the St. Lawrence River system. And so it's really a large river basin. And unlike other large river systems of the world, you know, if you look at this, there's a huge fraction of the surface area that is taken up by lake surface area. And that results in the need to represent complex processes like overlake precipitation or evaporation, like what you're seeing here. This is a cold winter day a few years ago when you can see a lot of evaporation happening across the lake. So I think this is a good image for demonstrating kind of the complexity of the system. Okay, so the Great Lakes are complex. They're also home to a large population of people. If we think of the coastal watershed communities, these are plotted here. This is a graphic from the Great Lakes Observing System. And if you look at the Great Lakes counties, there's about 27 million people on the US side of the basin alone. So I don't know, I don't think a lot of people think of this as a coastal region with a coastal population, but it's a very important coastal region for our nation. And, you know, there's major population centers. If you go from west to east, you're looking at Duluth in Minnesota, Milwaukee in Wisconsin, and keep going. You have Detroit, Toledo, Buffalo, Toronto in Canada. If you go further downstream on the St. Lawrence River, then you'll find Montreal. So there's some major population centers in the region. I mentioned in the opening slide that the Great Lakes are part of the St. Lawrence River system. And, you know, for those of us in the Great Lakes, we see the bumper stickers of the Great Lakes. We don't often see the image as part of the St. Lawrence River Basin. So that's shown here in the upper left. So a large portion of the basin is really, you know, part of that St. Lawrence River Basin. And on the lower left, this is showing the elevation profile going from most upstream, which is Lake Superior, moving downstream to Lake Michigan and Lake Huron. I'm actually going to be referring to those two lakes as one, Lake Michigan Huron, and that's because those two lakes are hydraulically connected at the Straits of Mackinac. Downstream from there, we get to the St. Clair River, which flows into Lake St. Clair and then Lake Erie, and then flowing over the Niagara Falls into Lake Ontario. And then from Lake Ontario, we go to the St. Lawrence River and the Atlantic Ocean. One thing I'd like to point out on this slide is it helps me to understand how each lake can impact the other lakes. So if you look at Lake Michigan Huron, Lake St. Clair, Lake Erie, those three lake levels are going to impact the flows in the connecting channels between those lakes. So for example, if the lake level of Lake Erie is high, that's going to end up slowing down the flow in the Detroit River, which is then going to impact Lake St. Clair. So the lake to lake difference in level in those lakes is going to impact the flows in the rivers and thus impact the other lakes. So it's really a full combined system that you have to look at. It's different for Lake Ontario. The level of Lake Ontario has zero impact on the upstream lakes, and this graphic shows it quite clear why that is. You would have to be able to climb up over the falls for Lake Ontario to impact the other lakes. Also shown on this slide on the right are three images that show the three locations where the flows in the connecting channels are regulated. So the most upstream place where there's regulation is the St. Mary's River, and that's at Sault Ste. Marie, Michigan, Sault Ste. Marie, Ontario. And so there's regulation there. There's regulation in the Niagara River. I will say that the regulation in the Niagara River, that is not impacting the total amount of flow through the Niagara River. It's really just impacting the allocation of flow through the falls and through the hydropower facility. But the total flow is essentially the same as what it would be without regulation. Then furthest downstream, there's regulation of the St. Lawrence River flows at Cornwall, Ontario, and Messina, New York, at the Moses Saunders Dam. So that's shown for the downstream. The regulation is conducted by the International Joint Commission. So the International Joint Commission is comprised of commissioners from the United States and Canada, and it's charged with managing the Great Lakes in a sustainable manner that balances the needs for competing interests. So with respect to hydrology, this really takes the form of managing the outflows of Lake Superior through the St. Mary's and outflows of Lake Ontario through the St. Lawrence River. The IJC, the International Joint Commission, was established through the Boundary Waters Treaty of 1909, which is really the foundation for sustainable water management in the Great Lakes. So the Army Corps of Engineers chairs the boards of control on the US side, and NOAA is involved by supporting the IJC through chairing the Research Coordination Committee, and NOAA also has a seat on the Great Lakes Adaptive Management Committee. In addition to that, NOAA has historically provided research and development of models that are used by the boards of control, and that's primarily through a unique research to operations partnership between NOAA, GLERL, and the Army Corps of Engineers Detroit District Office. So for example, one component of the technical support that the Army Corps provides to the IJC is the provision of seasonal forecasts of Great Lakes water levels. Those forecasts rely to some degree on models and data that are products developed by NOAA. NOAA also provides the gauge data that we use to get our lake-wide average water levels. So here's a map that GLERL produced that shows the NOAA gauges on the Great Lakes in blue, and then the Canadian gauges that are operated by the Canadian Hydrographic Service in green. So in NOAA, those would be operated by co-ops. And so the gauges that we use to compute our lake-wide average water levels are highlighted here as the solid dots with the circles around them. So those are the gauges that we consider to be, a good network of gauges in order to compute the lake-wide average water levels. Army Corps computes those lake-wide average water levels on the US side, and Environment and Climate Change Canada computes those on the Canadian side. We then come together and coordinate monthly data. So all of that data is in agreement between the US and Canada. And this is the result. So this is a lot to look at on one screen, but here what I really want you to take a look at is the patterns that you see, not so much the numbers. The numbers are available on the Army Corps website and on the GLERL website. So, but here I just want you to look at the patterns. This is showing our coordinated monthly mean lake-wide average water levels going back to 1918. So our coordinated data set goes back to 1918, so just over 100 years of data. The blue lines are the monthly mean lake-wide average water levels, and the red horizontal line is showing the long-term average level. And anytime I show multiple graphics, I'm going to start with Lake Superior on the top or first and end with Lake Ontario, so just going from upstream to downstream. So there's a couple of things that stand out when you look at the patterns in here. The first is that you see a seasonal cycle. You see high water levels in the summer, you see low water levels in the late fall, early winter timeframe, and that's a typical seasonal cycle that's fairly predictable with some variability that's not less predictable. And then the other thing that stands out is that throughout the 100 years of record, we do see periods of highs and periods of lows. If we look recently, the thing that stands out to people who have lived here for a few decades is they will remember that there was a very long period of very low water levels, especially on Lake Superior and Lake Michigan Huron. That period had started at the end of the 1990s and continued until the early 2010s. It culminated in a record low on Lake Michigan Huron at the end of 2012 and beginning of 2013, and it included a record low on Lake Superior in 2007. Since then, the lakes have really seen a very dramatic rise. Between 2013 and 2014, the lake saw a record-setting two-year rise. So that was the largest rise on record, largest two-year rise on record. And since then, we've had just very high water supplies to the lakes, and we've seen record or near record high water levels on all of the lakes in 2019 and now 2020. Okay, so in terms of what drives water levels, the first thing I pointed out on the last graphic was the seasonal cycle, so the within year cycle of water levels. And in a typical seasonal cycle, we have low water levels in the winter and high water levels in the summer. So that's shown here. This is just a generic lake cycle. The timing will vary somewhat from lake to lake, but in general, it looks like this. And that's really driven by the hydrologic cycle. So in the winter, precipitation is primarily falling as snow. It's accumulating on the land surface, so there's not as much runoff as we have in other seasons. Then in the spring, temperatures start to warm. We start to see high amounts of runoff into the lake. And in addition to that, we have more precipitation that's falling as liquid precipitation. So that is running off more quickly into the lakes. In the summer, we tend to have a little bit of a drought later in the summer, but more importantly, what's happening in the summer is that the sun is transferring energy to the lake surface. And that's very important because then in the fall, that energy exchange is really what's going to be driving evaporation. So evaporation is driven by a temperature difference between the surface water temperature and the air temperature. So in the fall, the lakes are really relatively warm compared to the air. And so we start to see evaporation. And unlike other large river basins of the world, evaporation from the surface of the lakes is a major component of the water budget. And so it's something that needs to be reflected when we're looking at the hydrologic cycle. And I like this image here because I get asked the question of why we have more evaporation in the winter than in the summer, and I think this demonstrates it really well. This is actually the day before Valentine's Day this year, in February. So in January, we had a warm January, we had a warm December. Surface waters were really pretty warm and wide open. And then in February, we started to see some cold blasts of air. If you remember, if you were in the region, on Valentine's Day, we had a pretty cold Valentine's Day. So this is showing February 13, 2020, a beautiful MODIS image, and you can just see that evaporation coming up from the lake surface. And some of it's going to be coming back down as lake effect snow, but some of it is going to be leaving the basin. So I've talked about precipitation, evaporation, and runoff. We talk about those three things together collectively as net basin supply. So that's the evaporation from the lake surface, the precipitation over the lake, and the runoff into the lake. Those form the net basin supply, and when the net basin supply plus the inflow from the upstream lake is larger than the outflow to downstream lake, that's when water levels go up, and vice versa. So it's just a water balance there. Recently, we've had extended period of very high net basin supply. And I'll walk you through this graphic before I jump into other similar graphics. On the left, that's just a snapshot of that long-term hydrograph for about the last 10 years or so of data. So those are just the water levels on the lake. On the right side, you're looking at Lake Superior data. The top panel is showing the net basin supply on an annual basis, and it's showing the deviation from average net basin supply. So below average net basin supplies are red bars pointed down, and above average net basin supplies are blue bars pointed up. And on the bottom panel, I have water levels plotted. So those are the monthly mean lake-wide average water levels for about the past 10 or so years. So the thing that stands out when you see this is that we have a period of rising water levels that corresponds to a long period of above average net basin supply. In fact, all the way back to 2013, we're seeing that our net basin supplies were above average each of those 7 years, and in fact, well above average in several of those years. So now that Lake Superior plot is here in the top left, and I also show Lake Michigan Huron on the top right, Lake Erie and Lake Ontario on the bottom. And the story is really very similar across the Great Lakes Basin, where more often than not, we're seeing above average net basin supply. So on Lake Michigan Huron, 5 of the past 7 years had very high net basin supply. On Lake Erie, 6 of the past 7 years had above average net basin supply. And on Lake Ontario, 5 of the past 7 years had above average net basin supply, and that's on an annual basis. I'm not going to spend a lot of time going into all of the components of the water cycle, but to me, the most important piece of it that we've seen in the past several years has been enhanced precipitation. This is a table that I compiled using the tools at the NOAA National Center for Environmental Information Climate at a Glance page, which allows you to build maps and tables showing rankings for precipitation and other meteorological variables. So I compiled these data points for the US side of the Great Lakes Basin. So this is showing the past 12 months, or the 12 months ending in 2019, so the year 2019, the 2 years ending in 2019, the 4 years ending in 2019, and the 5 years ending in 2019 for the US side of the Great Lakes Basin. And for all of those periods, they're the wettest of that they have on record, and that's out of 125 years of records. So the 5 years ending in 2019 was the wettest 5 years on record. So this has really been an ongoing story. I don't think we can compile that ranking beyond 5 years in that particular tool, but I think we would see above average precipitation if we went back just a little bit further, and I think we would see similar values if we looked at Canada. Okay, so we're at high water levels, and so now I'm just going to touch a little bit on the impacts in terms of what those variations really mean to people who live in the basin. And I know a lot of you are probably from the basin who are on the call, but some of you might not be as familiar. So this slide is showing two images from the same location. This is a recreational harbor in Grand Traverse Bay, which is on Lake Michigan. And the left side is showing a picture taken in January of 2008, so that'd be kind of in the middle of that extended period of low water levels. And my colleague Mark Breederland at Sea Grant took the same picture in May of this past year, May of 2019, of the same dock. And between those two dates, it looked like it was about a 5-foot difference in terms of looking at the data. If we look now, the difference is a little bit bigger. But you know, you look at this picture and you can see impacts in terms of access. So when you have low water levels, obviously this dock becomes unusable in that kind of situation. It doesn't look too threatening at high water levels when you see it this way. Calm water, just a big difference in levels. Now, those of you who live on ocean coasts may think, well, 5 feet of difference, we see that in a day from tides, or we see more than that maybe from tides. Here in the Great Lakes, that's a big lake level difference, and a lot of our infrastructure isn't necessarily built with that kind of difference in mind. We've seen that marinas have had to close periodically because their dockside power is inundated, for example. So this can have significant impacts in terms of, you know, infrastructure and access to the resources, that kind of thing. But when we add on to that meteorological conditions, that's when we really see the most dramatic impacts. The picture on the left is showing a storm last spring on Lake Erie. This is Stony Point on Lake Erie, a photo provided by the Port of Monroe director. And so this point received, you know, a lot of waves impacting them and a lot of flooding. When we have these meteorological conditions that set up storm surge kind of conditions, then you can see significant flooding, or SACE events that happen on the lake. Then you see significant flooding. And on the right side, this has become more of a news story recently in the region. Communities that are built on bluffs are seeing more erosion. This is a photo taken from a news source called MLive, and so this is the kind of stories that we've been seeing coming out of the basin. So when we have, you know, we have these kinds of, we have storms and waves and SACE events, and even erosion happens at all water levels. But when these things are happening at high water levels, they're much more impactful. They're impacting infrastructure and property and people in a much more significant way when we're at this high water level. I'm going to shift gears a little bit and talk about what kind of research gaps we have in terms of hydrology, going back to the title of my talk. Talking about the challenges that we face, and then go into work that is being done to try to address those challenges. And I'm going to focus on a couple different challenges. The first one is really talking about gaps in data. So there's gaps in observational data. If we look, for example, on the top left, that top left image is showing a map of meteorological stations that are used in the Great Lakes Basin for model development and forecasting and monitoring. Those in the US and the Canadian side of the basin, you see a lot of density, you know, over the US and parts of Canada where there's a lot of population. You see less density in some of the less densely populated regions. But in addition to that, If you look closely, you can see there's yellow dots over the lakes, and those yellow dots are the offshore observations that we have, and most of those are from seasonal buoys. So they're sparse, and not only that, but they're going to offer seasonal data. So we have large gaps in data over the lake. In addition to that, because the lake basin is essentially bisected by the international border, we often see discontinuities in data. If you look at the image on the lower left, that's showing the North American Land Data Assimilation System, NLDAS data compiled, aggregated for the year 2002. And you can see, so this was aggregated by my colleague Drew Grunwald, who was formerly at GLERL, and you can see that this really shows a dramatic discontinuity in data. You can see the international border in the data themselves. So that's an issue we see with many different data sets, and dramatically shown here. One of the ways that NOAA and the Army Corps and other federal agencies in the US and Canada work to address these issues is through participation on the Coordinating Committee for Great Lakes Basic Hydraulic and Hydrologic Data. That's a mouthful, so I'm going to be referring to it as the Coordinating Committee. The Coordinating Committee is comprised of engineers and scientists from US and Canadian federal agencies who are involved in collecting and analyzing data and developing coordinated products to support the boards of control for the IJC, the International Joint Commission. An example of a product that has recently come out of that coordinating committee is shown here on the upper right. This is a new binational precipitation data set that's housed by the Midwest Regional Climate Center, and it's available. It's got a web page that's interactive. This data set combines the state-of-the-art precipitation data sources from the United States and Canada. On the US side, it's using the multi-sensor precipitation estimate, and on the Canadian side, it's using the Canadian precipitation analysis. So this is a product that was supported by the coordinating committee, and a lot of effort went into it between NOAA and Environment and Climate Change Canada to pull these two data sets together and house them at the Midwest Regional Climate Center. And this product is a good example of our binational collaboration, and we're expecting this to become the main source of precipitation estimates for coordination of data between the US and Canada. Other things, the coordinating committee produces a lot of other data sets. For example, the water levels that you see are coordinated between those agencies. Okay, so in terms of discontinuities in data, the other thing I wanted to talk about is runoff data. The graphic on the left side is complex, but just focus your attention on the beige area of that graphic. So that represents the US portion of the basin that's ungauged. So there's no runoff estimates in those areas of the basin. Also, I guess it's worth noting that data, this graphic is essentially masking the Canadian side. A lot of times when we're doing runoff studies or other modeling studies, we're limiting ourselves to one side of the border or the other, and that's a result of that discontinuous data problem that I've talked about. So this is an example of that. And so in terms of addressing this issue, GLERL has been working with the NCAR National Water Model Development Team to expand the National Water Model to the Great Lakes, the Canadian Great Lakes Basin, the Canadian side of the Great Lakes Basin. So this recently that involved expanding the hydrofabric shown on the bottom, and the next version of the National Water Model is expected to have the Canadian portion of the simulations from the Canadian portion of the Great Lakes Basin. In addition to that, GLERL has been involved in providing runoff estimates across the Great Lakes Basin through the development of an earlier model called the Large Basin Runoff Model, and that model is an example of one of the forecast systems that was developed at GLERL and is now operational at the Army Corps, and that's used in our water level forecasts. So this expansion of the hydrofabric and the national water model to the Canadian side of the basin, it's a major advancement in runoff modeling for the Great Lakes because it provides us a new source of total runoff to lakes, but it also provides new source of flows, riverine input to advance coastal forecasting. And that kind of leads me to this next slide, describing work beyond what I've done with Army Corps and GLERL, but talking about the integrated modeling efforts at GLERL. So in the previous slide, I showed advancements in runoff modeling across the Great Lakes made possible by the National Water Model. Now that fits in with some of the integrated modeling efforts by GLERL. This slide is showing the black arrows are showing all of the ways that GLERL is working on coupling models. Specifically in terms of hydrology, a major focus has recently been coupling the National Water Model with the Great Lakes Operational Forecasting System output. And that's expected to improve coastal forecasting. And as part of that project, we've been evaluating precipitation data sets like the NLDAS data that I described earlier, and working to improve coastal coupling between national water and FECOM. And so I think this is a big advancement in terms of forecasting and simulation. When we look at the seasonal forecasts that we're able to put out for the coordinated forecast between the Army Corps and Environment and Climate Change Canada, that forecast is the monthly mean lake-wide average water levels. And so we're not able to simulate the nearer term impacts or effects that are important on a shorter time frame, such as flooding kinds of impacts. So that's something that is an active area of research at GLERL. So I did promise that I would be sharing the latest forecast from the Army Corps. So I'll talk about that next. One of the inputs one of the pieces of information that we look at and use to inform our forecasts is the NOAA Climate Prediction Center's seasonal outlooks. And so this is the latest seasonal outlooks. On the top two panels is showing the temperature and precipitation outlook for April, the month of April, and on the bottom it's the three-month outlook that integrates April, May, and June. And so when you're looking at these graphics, on the left, the reds are showing a likelihood of being above average temperatures. The blues are likelihood of being below average temperatures. And white color with an EC means there's an equal chance of being above or below average temperature. And similar thing on the right, where green is likelihood of above average precipitation, and brown is likelihood of below average precipitation, and white is equal chances. So when we're looking at April, we're seeing potential for warmer than average April, but not a lot of guidance in terms of precipitation, with the exception on the very west end of the basin, touching Lake Superior, we do see a potential for above average precipitation. And then on the bottom panel, looking out further, combining April, May, and June, we do see a likelihood for a wet spring and a potentially warm spring. So our forecasts are, I'll be talking through our forecasts next. They're available, the Army Corps forecasts are available on the website that's listed on each of the next several slides, or you can Google Great Lakes water level forecast Detroit district and you will get there. So this is Lake Superior. I'm just going to walk through this in detail before I go into the other lakes because all of the graphics contain the same kind of information. So the red line that goes back to April 2018, that's showing the observed monthly mean lake-wide average water levels from April 2018 to March 2020. The blue dashed line is showing the long-term average monthly mean lakewide average water levels. So when you look at the blue dashed line, that kind of gives you an indication of what the seasonal cycle, a normal typical seasonal cycle would look like. Above and below those lines, you see horizontal black lines with numbers. Those are showing the record high water levels and the record low water levels in the years that they occurred. Going out into the future, the green dashed line is showing our projected level from the coordinated forecast. We coordinate the forecast between the Army Corps and Environment and Climate Change Canada, and that green forecast is showing what we think is the best estimate of the forecast. The red shaded area behind that is showing the uncertainty around the forecast, and that uncertainty is essentially built using historical net basin supply sequences. So if we look at this forecast, you can see where the green line is essentially, for the most part, below those record highs. I'll get into the forecast in more detail next. So here's that same graphic. I just added some information to it. The new record highs that were set in 2019 and 2020 are shown in red circles, and the months at which we tied record highs are circled in kind of an orangey color. So our latest forecast was issued at the beginning of this week, and our forecast is showing that Lake Superior will be in its period of seasonal rise until August. And we're predicting that the Lake Superior will be within a few inches of record high water levels throughout our forecast horizon, which goes through September. One thing that you'll note as we go through the forecast is that they are all predicting above average water levels, and part of the reason that we're predicting very high water levels to continue is because we're starting at high water levels. So the monthly mean lakewide average water level for March was similar to last year's level. It was about 2 inches below the record high level. On Lake Michigan Huron, in 2019, we actually didn't see new records set in 2019. We came pretty darn close earlier in the year, but we didn't set new records. One thing I want to point out in this graphic is you can see a very steep seasonal rise in 2019, followed by very little seasonal decline. We actually saw quite a bit less seasonal decline than normal. I think it was about 5 inches seasonal decline compared to an average of about 12. Part of the reason for that less than normal seasonal decline was the warmer than average temperatures that we saw in the late fall and early winter. Those warm temperatures resulted in earlier enhanced runoff, as well as our models indicating that there was less than average evaporation, especially in December and January. So over the next 6 months, our forecast is predicting that the Lake Michigan Huron will be in its seasonal rise until July. It will be at or above record high levels throughout the forecast horizon, and it's important to note that the lake was 14 inches above last year's level in March. So that's really setting us up quite a bit higher than last year, and that was 4 inches above the record high. Okay, this is Lake Erie, and on Lake Erie, we saw quite a number of new records set in 2019 and 2020. Really, between May and September, we saw new record high water levels each month. And then again in February and March, the lake set new record high water levels. In our forecast, we're seeing that the lake will continue its period of seasonal rise this spring, but then begin its normal summer decline. It's forecast to be within a few inches of record high water levels throughout the forecast horizon. And note also that the March level was about 12 inches above last year's levels. So that was about 3 inches above the record high. Now, the furthest downstream lake, Lake Ontario, saw new record high water levels in June and July. I'll note also that in 2017, the lake set new records. So these 2019 levels were above those 2017 records that were set. And so our axis doesn't go back to 2017, but that lake has seen significant flooding in 2017 and now again in 2019. The lake is forecast to continue its rise this spring before declining in the summer. The forecast suggests that new record high water levels aren't likely, but the March level was about 8 inches above last year's level, which was about 7 inches below the record high water level. So those are the forecasts. I'll just give you a quick summary of what I talked about today before moving into a question and answer period. So in summary, I think it's, we have unique Great Lakes. Those of us who are from the Great Lakes really recognize that this is an important resource. It's the world's largest source of surface fresh water. It's home to unique relationships, one of which is the research to operation relationship between NOAA and the Army Corps to support binational water management. And in recent years, we've really seen a dramatic change from very low water levels to record or near record high water levels in 2019 and 2020. The lakes are unique, which poses unique challenges. And I focus specifically on a couple challenges related to gaps in observational data that result from both the large lake areas themselves and the international border, and as well as ungauged areas in terms of runoff simulation and also because of the international border. I talked about the importance of forecasting beyond just lake-wide average monthly mean levels. It's important that we see there's challenges related to coastal flooding, coastal erosion. Those things require coastal coupling. NOAA GLERL activities to address these challenges in collaboration with other federal agencies like the Army Corps is to work on building the binational data products that would enhance this kind of monitoring and forecasting through participation on the coordinating committee, work to expand the national water model being conducted with an NCAR team for the Canadian side of the Great Lakes Basin, and then subsequently coupling the national water model with biophysical and physical models to predict impacts. And lastly, just looking at the forecasts going out the next 6 months, we really are expecting another season of very high water levels. So we're expecting conditions to be similar to or potentially above where we were last year. And that's all I have. So I think Katie's gonna take some questions for me.
Yes, thank you so much, Lauren. That was a wonderful presentation. As a person from Michigan originally, I was very, very engaged in this. We do have numerous questions that people have been asking throughout the talk, so I am going to move through those now. Scott is curious if NOAA operates and maintains the network of Great Lakes gauges. For most of NOAA NWS hydrology programs, river stream, even mini tidal gauges, they're operated and maintained by the USGS. Does the USGS play a role in maintaining operating the Great Lakes gauges?
There's gauges that are operated by both. So like the gauges that we use to compute lake-wide average water levels, those are operated and maintained by NOAA. We rely on USGS gauges and even Army Corps gauges for connecting channels and flows in the connecting channels.
Wonderful, thank you. Denwood was saying that he just realized shallow water mussels are significantly impacted by big water level changes. Do you know if this is true?
That's a good question. I don't know. I'm not a biophysical modeler, but I think that there would be some light attenuation issues there, but that's really outside of my expertise.
Okay, thank you. Eric wanted to know, would sea levels and waves from satellite almetry be helpful to you?
Would sea levels and waves be helpful to us from an observational standpoint? Yes, I think that there's use in additional data. In terms of water levels, we are looking at a network of gauges, which seems to be good for predicting things on a lake-wide basis. But I know there's effort to look at water levels, for example, using gravity, like the GRACE sensors. And so any additional data is always going to be helpful in understanding not just the lake-wide average, but potentially how levels vary across the lakes.
Great, thank you. Why do you use such a long average? Judith wants to know 120 years, and why not look at just the last 30 years or shorter, given the climate changes that are occurring?
Yeah, that's a good question, and one that I've been thinking about for a while in terms of looking at. I think it's important to look at the long-term record to understand how things fit now relative to the past. You know, we do see we are setting new records, so that's important to know from the long-term perspective. When we look at using information from the historical record for our forecast, for example, one thing that I've been looking at recently is adjusting the period of net basin supply data that we would use to inform the uncertainty around our water level forecast. So for example, reducing that to something more aligned with the way that we look at climate data, you know, looking at the last 30 years or so.
Great, thank you. For the projections for Lake Ontario, are those independent of water level management, or do they include current water level outflows? Carolyn wants to know.
The projections that we put out in our 6-month forecast that's coordinated, and also the weekly update that we provide at the Army Corps, those are incorporating the regulation decisions that are coming up, as well as, you know, as we simulate beyond the coming regulation period, we would be simulating expected regulation decisions. So they do incorporate regulation in the routing of net basin supply to get water levels.
Gotcha, thank you. I'm not sure if you know this one, but Craig asks, are there estimates in dollar of damages to property and infrastructure from high water levels over the last few years? And would you know where that information could be found?
I believe there have been some estimates. I believe I've heard some numbers when I've sat in, for example, on calls with the Great Lakes Climate Quarterly reports. I don't have those numbers in front of me, and I'm not sure quite where they came from, aside from maybe news sources. But there may be some of that in those Great Lakes Climate Quarterly reports, which describe impacts in, you know, in the past 3 months. Okay,
thank you. Shana wants to know, have you looked at GPM data from NASA for precipitation and water level data?
I don't think we have. I haven't, but I'm not sure if somebody else in our area has. I'll take note of that.
Okay. Vinya wants to know, how far ahead is it realistically possible to forecast future water levels in the Great Lakes? Do uncertainties surrounding yearly seasonal runoff and precipitation make forecasting lake levels harder than forecasting, for example, sea levels?
Yeah, that's a good question. I think we do, in terms of forecasting water levels, we go out 6 months in the official forecast, and that you can see there's considerable variability or considerable uncertainty. That's primarily driven by uncertainty in the seasonal climate that we're seeing. So one thing that does make it easy from, you know, the modeling perspective is, at least on a seasonal basis, we expect there to be a seasonal cycle. That seasonal cycle is going to be a little bit different from year to year. For example, on Lake Michigan Huron, we only saw 5-inch decline compared to 12-inch decline, and we had a really big seasonal rise. But we do know there's going to be some seasonal cycles, so making those seasonal projections is feasible. Going out beyond the 6-month horizon, it really becomes very difficult. We do have a product at the Army Corps that is kind of, it's more of a scenario-based tool where we look at what water levels would be under all of the different water supply sequences that we've seen from the past. And that is informative, even though we don't expect that we would have, you know, that necessarily represents the expected water supplies that we'll see. It does show us, you know, the potential, the maximum potential or minimum potential, at least from what we've seen in the past. So for example, on that product, when we simulate out 12 months, the latest publication of that product shows that even if we have the driest water supply sequences that we've seen, you know, in the whole historical record, we would still be pretty well above average on Lake Michigan Huron and most of the lakes. And so that's informative, you know, from the point of view of understanding the memory of the lakes. So the lakes, because it takes time for water to move out of the lakes, and to fill the lakes, they really do have a memory that allows us to say, if we're at really high water levels right now, we're really probably going to be at high water levels at least for the next 6 months to a year. It would take an extended period of low water supply to bring us down to low water levels. So from that point of view, perhaps it's a little more predictable. In terms of climate impacts, it's a little bit less predictable because you know, we just don't expect water levels to keep going up for, you know, as a result of climate change. We think about it more in terms of the changes are impacting precipitation, runoff, and evaporation in different ways. And so we need to aggregate those impacts through net basin supply. And so what we do need more research in that area, but what we communicate is that we need to be prepared for a future with high water levels and a future with low water levels.
Thank you. Dennis is asking, prior to the last 7 years when Great Lakes water levels were low for several years, was this due to lower than average precipitation into the basin?
So the period from about 1998 to 2012 was that period of very low water levels. And that was because of below average water supply, net basin supply to the basin. There has been research that's shown that there was a change in evaporation in the lake energy content. And so there was some evidence of enhanced evaporation during that period. And so that definitely played a role in those low water levels.
Great, thank you. I'm not sure if you can answer this question, but do you know how high water levels have affected the operations of navigational locks in the Great Lakes?
So the locks are operated for you know, ship traffic, and those are there. In terms of operation of regulation, like the regulation of flows, that's a bit of a kind of a different thing. If we're looking at the St. Mary's River, the regulation is conducted using Plan 2012, which does take into account the lake levels on Lake Superior and Michigan Huron, and attempts to first simulate, you know, natural differences between the lakes, then do balancing to balance the impacts on those lakes. And so there's some impact of the water levels on the regulation. I will say that while there is some goal in terms of regulating the difference between the lake levels, the ability to actually do that regulation is limited. The regulation is really impacting the flow in the St. Mary's River, which is only to some degree impacting the lake levels. The lake levels are really being regulated by Mother Nature, with, you know, in terms of the precipitation, runoff, and evaporation.
Great, thank you. We have a question about slide 20, if you would go back to that. They're wondering if ungauged, does this mean stream flow gauges or water level gauges?
Oh, I was referring to stream flow gauges.
Thank you for clarifying. Okay, let me look for another question. Along with future activities to couple models with biological and physical factors, is there a hope to try and generate flood forecasting models or tools?
Yeah, I believe that's one of the major goals of coupling the National Water Model with FECOM is to be able to forecast impacts such as flooding, especially related to storms. You know, when you combine storms in addition to lake levels.
Great. I'm going to grab a few more questions here. We are about 5 minutes to time. Deborah wants to know, do we know what the global ocean and atmospheric circulation patterns are that drive the decadal lake level changes?
That's a good question, and I think that's an area that we don't have a lot. I think there's some other scientists, for example, like GLERL, who might be able to step in and help with that question in terms of understanding teleconnections and how they impact hydrological conditions in the basin. But overall, I think that's an area that we do need more, where we do need more research to understand how what we see at the lakes is being impacted by the global conditions.
Okay. Hayden wants to know, what challenges does quote unquote new bathy as a result of higher water levels present in regards to coastal coupling?
That's a good question, and probably something outside of what I would be able to answer, more for one of the hydrodynamic modelers who's involved in coastal coupling here.
Okay, no problem. I'm going to grab a few more questions. How do you factor upstream and downstream conditions lake to lake in your models or into your models?
So when we look at lake to lake routing, we use a coordinated Great Lakes regulation routing model, which incorporates not only the regulation logic for the locations where there's regulation, but also rating equations for estimating flows through the connecting channels using lake to lake differences. So those are really based on rating equations.
Okay. And I'm going to grab one more question. How are weather pattern changes, transitions between seasons and year to year involved in lake level forecasts?
So in terms of looking at weather patterns, we really just use look at the seasonal forecasts that we get from the Climate Prediction Center, and then we look at the equivalent product from Canada in terms of seasonal forecasts. We take that information, we use it in a couple different ways. The first way is to kind of inform us in terms of what we're expecting. You know, are we expecting it to be wet? Well, we'd probably want to be looking at model output that has wet conditions. So that helps us to kind of evaluate the net basin supply forecast that we're looking at. In addition to that, some of the models that we use seasonal projections more directly. For example, with the CPC's seasonal climate outlook, we actually take that climate outlook in terms of like the probability of being above or below average precipitation and temperature, and we use that to adjust our meteorological forcings, which are based on climatology. So we're using an ensemble of meteorological forcings in one of the models that we use. We use an ensemble of meteorological forcings, and we adjust that ensemble by weighting it so that it matches as good as we can to what we're predicting in terms of likelihood of being above or below average precipitation or temperature across the basin. We also use the North American multi-model ensemble predictions of precipitation and temperature to inform one of our forecast models, which is actually a regression model, that is a regression between historical precipitation, temperature, and the coming months, the coming 6 months precipitation, temperature, and also the historical net basin supply. And we use the North American multi-model ensemble. Currently, we just use the median forecast from that to inform that regression model output directly. And I think the plan is to build in that full ensemble to be able to get more representation of uncertainty from that seasonal projection.
Thank you so much, Lauren. We are at time. My one last question is, will you be making this PowerPoint available, or would you mind making this available?
Yes, I think, can you, you will be providing this on the YouTube channel. Is there another way to share it?
Yeah, I can make this so that everyone can get access to it, or they can email library.brownbag@noaa.gov to get access to it. So I will make sure everyone knows that. Also, I would like to apologize to everyone online. We had a major onslaught of questions. I tried to pick and choose and spread that out. If you asked a question and I did not ask it, I will be passing those on. Thank you. And thank you everyone for joining us today, and have a wonderful rest of your day. Thank you, Dr. Frey.
Thank you.